Good afternoon, I'm Giacomini and I'm going to present a work that deals with the numerical solution of turbulent pipe flows where a particular stabilization strategy based on Tikhonov regularization has been applied. Pipe flows are defined as internal flows inside pipes, and they represent a challenging branch of fluid dynamics since pipe flows are even not fully understood in complicated situations. And just to fix ideas, some examples of challenging pipe flows are the multi-phase flows or turbulent flows. For example, this work deals with a turbulent flow, or flows where cavitation occurs, or flows with periodic variation, so the so-called pulsatile flows, transient flows, or even flows involving non-Newtonian fluids. And the importance of pipe flows is due to the fact that they are involved in some relevant real-life application, for example, the transport of petroleum fuels, of district and drinking water, and district heating, or applications as cooling systems. The study of pipe flows in our group has started with an application in the geothermal energy field. In this field, I have also discussed my PhD thesis. In particular, geothermal energy is a renewable energy resource that is based on the exploitation of the heat stored into the earth by the humankind. And the devices that allow this exploitation are called geothermal exchangers. Such devices consist in a pipe and a carrier fluid that circulates within the pipe. And these exchangers allow the heat transfer between the fluid into the device and the surrounding soil. And the operating principle is that the temperature in the underground is constant all over the year. And such exchanger can be placed into the soil in different layouts, as you can see in the picture from the left. And also, such devices can have different geometries, and in the picture on the right you can see one possible configuration, which is the U-curved pipe. Now we focus our interest on a pipe flow into a rectilinear pipe. Here we have the classical formulation of a pipe flow problems in terms of fluid dynamics laws. In particular, the first equation is the momentum equation, also called the Navier-Stokes equation, and the second equation is the continuity equation. Then, the previous equations are endowed with suitable boundary and initial conditions. In particular, the boundary conditions prescribe the velocity field at the boundary, and here the boundary have been denoted by gamma. So we have gamma in for the inlet phase, gamma out for the outlet phase, and gamma W for the wall of the pipe. On the other hand, the initial condition prescribes the velocity field at the initial time step. Now we briefly analyze the approximation of the flow problem that we have defined. I will just show the fundamental steps. The approximation scheme is based on the Galerkin finite element method, so we suppose to discretize our domain omega by means of a tetrahedral mesh, whose nodes consist in the 4 vertices of each tetrahedron and the 6 middle points of its edges. So we define 2 bases of finite elements. In particular, one basis is made of second-order polynomials that we denote with CH, and the other basis is made of first-order polynomial that we denote with phi k. And we use the first basis CH to represent the approximation u tilde of u, so the approximation of the velocity field. While we use the second base, so pk, to represent the approximation p tilde of p, so for the pressure field. Regarding the time discretization, we use the backward finite difference to approximate the time derivative, so we have a procedure that resembles the implicit Euler scheme. Moreover, we have a nonlinear term in the Navier-Stokes equations, which is the advective term. So we linearize this term by means of the linearization technique for Auxine problems. In particular, we substitute into the U-grad operator the velocity with the velocity field evaluated at the previous time step. We manipulate the equations of the weak formulation of the problem by applying the Green's identity, the divergence theorem, and we obtain this final linear system where the coefficient matrix AN is made of three main diagonal blocks. Each block is made of three matrices. M is the mass matrix, S is the matrix coming from the discretization of the Laplacian term, and N is the matrix coming from the discretization of the advective term. Then we have matrix L, which comes from the pressure contributions. The coefficient matrix AN depends on the time step n, since also the matrix n, so the advective term, depends on the time step. Then we have xn, which is the unknown vector, and it consists in the coefficients of the velocity and the pressure in the finite element representations of velocity and pressure fields. Finally, Bn is the known term. Moreover, we also apply a fixed point iteration strategy in order to provide a satisfactory refinement of the solution at each time step. All the details about the discretization procedure can be found in the paper reported at the bottom of the page. In conclusion, the computation of the solution of this linear system is not a trivial task, since the coefficient matrix, AN, is not positive definite, it is not symmetric, and it has a high sparsity pattern and also zero block on the main diagonal. Moreover, the system is ill-conditioned for high Reynolds numbers, so where turbulent flows are considered. Thus, the computation of the solution of this linear system requires the application of some stabilization strategy. The stabilization strategy that we propose is based on Tikhonov regularization. Tikhonov regularization is commonly used for ill-posed problems in the sense of Hadamard, so it works for compact integral operators. And here we have the Tikhonov functional written in coordinate in the most used formulation. And the minimum of this functional gives the solution of the regularized problem. Now, the idea is to apply the Tikhonov regularization as a stabilization strategy for the computation of the solution of turbulent flows. In fact, turbulence creates a kind of ill-posedness to the flow problem. Why that? Because in turbulent problems, the advective term dominates the diffusive term. And as turbulence increases, Reynolds number increases, and the advective term dominance increases. And this creates a difficulty in the prescription of boundary conditions. In fact, boundary conditions should be prescribed in accordance to the nature of the new turbulent problem, or better, of the resulting turbulent problem, which is an advective problem. So, where the first order dominates the second order terms. The Tikhonov functional that we propose is written in the bottom of the page, and it is made of two Tikhonov matrices, J1 and J2, and they are defined in accordance to the nature of the problem. So J1 is defined from the mass matrix, and J2 is defined from S matrix, so from the diffusive term. Then the Tikhonov parameters, lambda, are not constant in this functional, but they are matrices because they depend on the diagonal block. It can be shown that the minimum of the previous Tikhonov functional exists and it is unique, and it can also be shown that to find the minimum of the Tikhonov functional means to find the solution of this system. Now, just a few observations about the parameters, the Tikhonov parameters lambda 1 and lambda 2, and they must be chosen small enough to obtain a slightly perturbed solution of the normal equations, but also sufficiently large in order to obtain a well-conditioned system. Moreover, we have observed from simulations that once we fix the characteristic velocity of the flow problem and the discretization steps, the Tikhonov parameters are quite stable. So they are quite independent from, for example, geometry variations. Finally, the coefficient matrix of this system has favorable computational properties. For example, it is symmetric and positive definite, and the action of this matrix can be efficiently computed by exploiting the sparsity pattern of the original matrix, or better, of the matrix of the original system, so AN. Before going into details of the numerical results, I give the characteristics of the domain and some physical parameters. So our domain omega is a rectilinear pipe with radius 0.016 meters and length 0.31 meters. We discretized the domain with a tetrahedral mesh with about 12,000 elements and 3,000 vertices. The characteristic velocity of the flow is 1 and the Reynolds number is about 40,000, while the initial velocity profile is null and the velocity profile on the inlet phase is equal to 0 for the first and second component of the velocity, while the third component is uniform and constant, equal to 1. Then we have the Tikhonov parameters used, so we have small constant parameters except for lambda 1, 3, which is the stabilization parameter for the third velocity component that has an exponential trend. Now we show the numerical results of the flow problem with the proposed stabilization strategy implemented in a Fortran code. On the left, we have a U-curved pipe, so a different domain, but we would like to show these qualitative results because it is quite interesting to observe the development of turbulence. In fact, it is clear the vorticity, and it is also clear the action of the inertia force that pushes the maximum of the profile towards the boundary at the bottom of the U-curve. On the other hand, on the right, we have a quantitative result, so we have the numerical profile along a cross-section of the rectilinear pipe, so our familiar domain. And here the average turbulence profile is good. It is interesting to compare our results with results obtained with different solving strategies. So we consider the well-known OpenFOAM CFD software, where our pipe flow problem is modeled by a RANS model. Here the domain is discretized by means of the finite volume approximation, and the solving strategy is based on PISO algorithm, which is a segregated solver that computes velocity and pressure fields sequentially. On the right, we have the qualitative results of two different simulations with OpenFOAM. In particular, for the pipe on the left, we have at the inlet phase a developed velocity profile along the third velocity component, while for the pipe on the right, we have for the third velocity component at the inlet the usual constant and uniform profile. Now we can compare our numerical results with the OpenFOAM results. In particular, we will exploit the empirical turbulence profile called 1/7 power law for the third velocity component, which is the axial velocity, so the principal velocity component. In all the three pictures, we have the red lines, which is the empirical profile, while the lines with the circle markers are the numerical results. In particular, the blue line shows our numerical results with the proposed Tikhonov stabilization strategy, and the green lines are results from OpenFOAM. So, in the picture on the left, our results, we have a very good agreement between the empirical turbulent profile and the average turbulent profile that we obtain with our stabilization strategy. In the picture on the right, again, we have a good agreement between the OpenFOAM results and the empirical turbulent profile. Perhaps these results are a bit worse at the beginning, so near the zero. While at the center, OpenFOAM doesn't perform well. In fact, in this case, it starts with an inlet profile, which is a parabolic developed profile, and then OpenFOAM is not able to develop a turbulent profile. In fact, the green line is quite far from the expected turbulent profile. In conclusion, I have shown preliminary results on a stabilization strategy for turbulent pipe flows based on Tikhonov regularization. But we would like to go deeper in the investigation of the effectiveness of the proposed method on pipe flows, both from the analytical and the numerical point of view. Besides, we would like to compare our method with the artificial viscosity methods. In fact, the artificial viscosity methods are applied to model the small scales in turbulence or shock problems, since these small scales cannot be resolved by a finite dimension discretized problem. So, the strategy of artificial viscosity methods consists in adding a term to a term containing the viscosity, and this acts as a stabilization strategy. And the added term is called artificial viscosity. But we would like to investigate the possible correlation between our method and the artificial viscosity methods, since also in our method the matrix lambda 2 could be seen as a kind of artificial viscosity. Finally, we would also like to extend our method to external flow problems. Thank you for your attention.